All right, it's 11:15. I think we'll get started. So take a look and see when the final is scheduled. There is an online section of this class too. You don't know many of those people because they're not here. But the final will be open Wednesday, Thursday, and Friday. So you can take the final anytime within those 3 days. But the caveat is that there will only be office hours on Monday and Tuesday because I don't do office hours during the final period. And so if that's an issue, let me know. If I know ahead of time, we can work something out. And remember, I'm always available for appointment office hours. But the way I think that we should handle this is that we'll have some extra office hours the last week of class. And we'll have some office hours on Monday and Tuesday, or you can make an appointment. So if you're planning to take the exam on Friday, you know, that's an issue because Wednesday and Thursday could be your study days, but I'm not going to be available to answer questions by email or anything else. And so why don't you think about what your schedule looks like? Think about all your finals, but I won't do office hours on exam days to make sure that things are fair for taking the exam, but I will have some extra office hours. So check that out. Take a look at your schedule, figure out when all your finals are and when you're going to do your studying. And then I'm happy to make appointments now for when you want to do your final studying, not on Saturday, Sunday. Those are days where we do our individual work. But if you want some more clarification the last week class, or you need a special time on Monday and Tuesday, just let me know. I'm happy to schedule those appointments. So that's the caveat. The final period will be open and flexible, but I won't be available during when the exam is open. So think about that and get back to me with if you want to tweak it in some way. Okay. Also, there's a homework due on Friday, usual PLAs, all that stuff. We have a couple of regular weeks. And I think if you're looking at the syllabus schedule, we've got 3 homeworks in this round before we have an exam. So take a look at when exam 4 is. We have one more regular exam, remember? And so from now until the end of the semester, it's a good time to plan out your approach. We have regular office hours. We have some people that take advantage of those, but if you need an appointment, again, I'm available. I'll try and be available by email, etc. Any questions or comments? Okay, so we talked a lot about ideal solution theory and entropy of mixing last time. And so remember, ideal solution theory, at least the change in entropy, the delta S of mixing, is based on the mole fractions and the number of moles when we have small molecules. And you want to remember what the assumptions are for ideal solutions. Flory-Huggins, the important part of Flory-Huggins is it's a volume-based calculation of the change in entropy upon mixing. Now, this is only the entropy part. There's no enthalpy part yet. Where is the enthalpy part in Flory-Huggins? So if we want to add something to do with interaction between molecules or delta H, what do we have to add to the Flory-Huggins to get that? Well, delta G is the whole expression, so it's delta GM equals some other stuff. But what parameter in Flory-Huggins talked about the interaction energies between the components?
I was going to say temperature.
It's not temperature. We add chi. So this is chi, which is called the Flory-Huggins interaction parameter. So in the parameter, it tells you about the intermolecular interactions. But for the entropy, there's no delta H or there's no chi in this. And so the important part of this slide is ideal solution theory, mole fraction in moles. That's easy. You know that. What's the delta H for ideal solution theory? 0. Perfect. Delta H mixing equals 0. That's built into the assumptions for ideal solution theory. And so if you want to know about interaction between molecules, that's built in to Kai for Florey Huggins. And what we're really talking about, or the way to sort of think about this, is the interaction of a polymer and a solvent. So if the polymer and solvent have strong interactions, or the polymer is really soluble in that solvent, what's going to happen to the polymer chain? Remember last time when we were calculating root mean square distances and valence angle models and sizes of things, we talked about coils that were expanded versus coils that were contracted. So for a highly soluble polymer, what's the coil of the polymer going to look like in solution? It's going to be expanded, right? So highly soluble polymers well, here, let me get a new slide just to start fresh here on a Monday. There we go. Highly soluble polymers, strong interactions, between solvent and polymer, and that leads to expanded polymer coils or globules. You know, something with a lot of interactions. There's going to be a lot of solvent surrounding that polymer chain because you have lots of solvent polymer interactions, and that's what makes a soluble polymer. For insoluble, or let's say low solubility polymers, we have weak or not many polymer solvent interactions. And that leads to coiled globules with just a few solvents around, tightly and it turns out that you can see this difference in polymers. So if you take a polymer and it's highly soluble in a solvent, this solution will generally be clear. So when you look at that polymer solvent mixture, it's going to look clear. It could be looking like honey or water. It's probably going to have a little bit higher viscosity than water, right? Because the polymer increases the viscosity. But this is a nice clear solution. So when those chains are stretched out, everything's really at the molecular scale, and you can't see molecules. They don't scatter light in the visible wavelength. However, when we have tightly coiled chains, some of these chains or some of these coils can be big enough to scatter light. And this is generally a cloudy solution. Or it's a colloidal solution or something like that. And so people who have figured out when polymers are soluble, when they aren't soluble, different mixtures of solvents, or solubility of polymers is a function of temperature, sometimes they look for this clear and cloudy solution to give them hints about, is the polymer all stretched out? Are there a lot of polymer solvent interactions? Or is the polymer tightly coiled up, where the polymer prefers to associate with itself and the solvent prefers to associate with itself? That's not a very soluble system. So the question is, how do we get a situation like this versus how do we get a situation like this? And there are a couple different ways or a couple different rules of thumb that we can think about for highly soluble polymers. So what's the general rule when we're talking about solubility or miscibility, which means those two components mix? What's the easy rule of thumb that we think about for mixing molecules? Like dissolves like. Perfect. That's why we talked about polystyrene being soluble in toluene, right? Those are very similar looking molecules. And so like dissolves like, we know that polystyrene is likely very soluble in toluene. Great, we can look at that, we can figure that out. And so if we take something like polyethylene and try and dissolve it in toluene, we have an aliphatic system versus an aromatic system, we're gonna have something that's probably more akin to low solubility, where we have polyethylene chains that just want to associate with themselves, and the toluene doesn't get in there and expand the coil. And so today we're going to talk about a quantitative measurement for like dissolves like. So that's an easy thing to remember, but we're actually going to put some numbers on it. And I think that's the gist of your second homework problem, but we're going to talk about that today. Any questions so far? All right. So this is just the delta S part of mixing for small molecules and polymers. And for the full Flory-Huggins, we have the delta G of mixing. Someone said we need a delta G. That's right. And here is the interaction parameter where we bring in now the interaction between the solvent and the polymer, or we bring together the interaction of two different polymers, because Flory-Huggins can also describe polymer blends as well. And so the question is, I mean, we can get the volume fractions, we can get the number of moles, all that stuff. The question is, how do we get this interaction parameter? And there's a few different ways to do it. All right. So we talked about these G12s, G22s, G11s, they are not so easy to look up. So we need to get a proxy for the enthalpic interactions of these small g's. All right. Oh, and we talked about polynipane. So get out your clickers. I think we're still on CG, but I'll maybe check the clickers this week to make sure we're on track. All right. So this is poly N isopropyl acrylamide right here. And so what is the dominant intermolecular interaction when we dissolve polynipam in water? What molecular interactions are we talking about? When water's involved, there's a pretty good guess what IMF we're thinking about. And so that's something to remember. 48. Let's see if we can get over 50. It feels like there's more than 50 people here. Here we go. All right. So hydrogen bonding, of course. And so you have this NH group on polynipam. That's a key hydrogen bond donor. And then you've got water right here. So you have a hydrogen bond acceptor with the lone pairs of oxygen. And so you have hydrogen bonding. So this is tricky because, of course, what's the dominant intermolecular, great, 52. What's the dominant intermolecular interaction when you have toluene and polystyrene? Just dispersion forces, right? So we can contrast that with, remember, toluene is benzene with the methyl group on it. Here's polystyrene. All you have is dispersion forces here. And so this is where like dissolves like, right? If we had to come up with a solvent that has a chance of dissolving polyethylene, what solvent might we pick? Based on your organic chemistry knowledge, what solvent would we pick to dissolve polyethylene? What's that?
Ethane?
Ethane is okay, but it's a gas at, sort of on the bench. But keep going. What molecule like ethane is a liquid?
Maybe hexane.
Hexane. That's a good one. Plus hexane. We add a couple more carbons, right? Or octane if you want. We add a couple more carbons and we get liquids. That would be a good solvent for polyethylene because hexane is like a 6-carbon little teeny version of polyethylene. It turns out that polyethylene is really hard to dissolve because it's so highly semi-crystalline. It's hard to break up all those crystals, but at high temperature, you can dissolve polyethylene in hexane. That's a system they use. And this is also dispersion as well. And so identifying hydrogen bonding is important because it's a really powerful force for solvating polymers. So polymers that are water soluble tend to take advantage of this hydrogen bonding interaction. And it's hard to say, well, like dissolves like, polynipam doesn't look anything like water. So you have to remember the other intermolecular interactions. All right. Next clicker question. This is a good one. Given that delta H is negative, remember if there's strong dipole interactions, delta H would be negative, right? And the observation that phase separation occurs upon heating. So in this slide, if you checked out the Wikipedia page for polynipam, as you heat polynipam, you get a cloudy solution. The polymer comes out of solution. You've got less polymer water contacts. As you cool polynipam, it goes back into solution and becomes clear. So you're using temperature to modulate the Gibbs free energy of mixing. So given that delta H is negative and the observation that phase separation occurs upon heating, what does this tell you about delta S of mixing? And this is sort of one of the key questions to make sure you understand how delta H and delta S work together. So we have delta G of mixing equals delta H mixing minus T delta S of mixing. So delta H is negative, right? What do we want delta G of mixing to be if we want something to be soluble? Negative. So delta G mixing less than 0 equals thermodynamically favorable for mixing. Great. And so how do we change the sign of delta G given this information? Delta S has to be negative as well, because if delta S is negative, it all depends on the sign of T, or we can raise and lower T, right? And so, wait, hold on. Yeah, delta S is negative, right? And so as we modulate T, we know that we can change the sign of delta S. Great. So how this works is that, say, let's see, since say temperature is small, right? So let me get on the right. Delta G equals delta H minus T delta S. So delta H is negative, delta S is negative. And so if T is low. So if T is low, T delta S is a small, negative T delta S is a small positive number. And if T delta S is a small positive number, and delta H is still a big negative number, delta G mixing can still be less than 0. So it's the balance of the negative delta H versus now if delta S is negative, this whole quantity is going to be positive, right? But our overall expression can still be negative if delta H is a bigger negative number than this as a positive number. That's a little tricky to see, right? However, it's easy to see if T is big, negative, let me put negative T, negative T delta S is a large positive number, which will eventually make delta G of mixing greater than 0, and this is unfavorable. And so that's pretty interesting because now you can counterbalance the effect of delta H of mixing and T times delta S of mixing in order to get different signs of delta G mixing depending on the magnitude of the temperature. Yes?
Temperature would never be negative, correct? Because we're in Kelvin.
That's correct. You're always in Kelvin, and that's the secret. You can never have a negative temperature, right? Because we're doing thermodynamic calculations, and so all of those work if you use absolute temperature. You know, you'll get them wrong unless it's a delta T. You'll get them wrong if you're using degrees Celsius. So, yes.
I'm a bit confused why delta S would be actually negative, because if delta G is going to equal less than 0, i.e. a negative number, then delta H is going to equal a negative number, and T is going to be constant. When you want delta S to be positive in order to have it be less than the actual number be more negative.
Yeah, so the key is that the key observation for knowing that delta S is negative for this situation is that the polymer is less soluble at high temperature, which means delta G mix is greater than 0 at high T, and delta G mix is less than 0 at low T. That's the observation. And then we have to pick a delta S that makes that true. So T is not constant high temperature. T is one number, 400, whatever it is. I think for polynitram, it's like 303 or something like that. And then low temperature, we can pick 273 or 275 so the water doesn't freeze, something like that. And so the observable is this. And the only way to make that true is that delta S has to be negative. If delta S is positive, what is the sign of delta G always? Always negative, right? And so if delta H is negative and delta S is negative, delta S is positive, delta G will always be negative. But that's not what we observe in the experiment. We see a change in solubility with temperature. That's very, very tricky. And so once you establish what's going on with delta H, whether it's positive or negative, you can think about, does the solubility change with temperature? And then what does the sign of delta S have to be in order to meet that observation? Some things are not soluble no matter what temperature you're at. And so you could say that the delta H is really, really positive. Right? They absolutely don't want to interact at all. And so you can think about how this would work or how to get the right sign of delta G, depending on what's going on with delta H and delta S. And that's, like I said, that's tricky because if one term is positive and one term is negative or vice versa, it all depends on the sign of delta H and delta S. Depends on signs of delta H and delta S. And this example of polynitram goes against our expectation, right? We usually think of delta S of mixing as positive. In a normal scenario, we always think of delta S of mixing as positive or negative. What do you think? You're mixing two things. You're creating more disorder, right? Delta S of mixing is usually positive. I mean, that's what we always think. We're creating disorder by mixing things together. But in these inverse solubility examples where things are less soluble at high temperature and more soluble at low temperature, it's usually that the delta S of mixing is negative for some reason. And the reason that the delta S of mixing is negative in this system is actually because of the water and the water intermolecular interactions and organization in terms of hydrogen bonding. That happens in water. It's a very strange fluid. You could study that in your future classes, but there's a little paragraph here to help you through that. Yes?
So what would we observe if delta G was 0?
Ah, that's very interesting. So at equilibrium, what would you see in the experiment? Well, okay, so eventually, you know, if you have something sitting like this, the delta G of mixing for for the polymer in the act of coming out of solution is positive. And then the free energy has to go to 0 because eventually you'll be at equilibrium. So you'll sort of wind up at equilibrium in the state that the solution's in. So I think it depends. It's going to depend on the temperature. Yeah.
What if before delta G is positive or negative? Like immediately when you mix them, the delta G is 0 from the get-go.
Well, in this example, so we could look up the delta H and delta S, and so there's a temperature at which if the delta G crosses from positive to negative, there's a temperature at which delta G is 0, and that's called the cloud point temperature, where you're right at the phase transition. So it's like, well, what it is, it's you're at equilibrium between the soluble and insoluble polymer, because ice has an equilibrium temperature, right? So 0 degrees Celsius, you can have water at 0 degrees Celsius, and you can have ice at 0 degrees Celsius, and the equilibrium is defined by the equilibrium between those two phases. And so I think in this cloud point example, you'd have the soluble polymer and the insoluble polymer, and they would be in equilibrium. And so delta G would be 0. Yeah, that is a very good question. But we could definitely calculate an equilibrium temperature because we know the sign process. Good. All right. Okay, so there will be questions where you have to think about what the delta H is and what the delta S is, and then justify whatever's happening with the sign of delta G. Okay, so there's a lot of aqueous, a lot of liquid phase separation that works on this principle. So back to these interaction energies. So it turns out that those small g11, small g22, small g12 are hard to calculate. So we need a proxy for that. And the proxy that we're going to use is called the cohesive energy density. And that's given the symbol delta squared. And if you take the square root of the cohesive energy density, you get what's called the solubility parameter. So delta is the thing that we're going to focus on. That is the solubility parameter, and it's derived from the cohesive energy density, which has this definition. It just tells us all of the various energies that hold together a condensed substance. If you take that and separate it, how much energy does it take to separate all those molecules to infinity? That's defined as the cohesive energy density. And so it's related to the molar enthalpy of vaporization. That makes sense because vaporization, you're separating things by a long distance, and there's a molar volume and RT in there in order to get the energy part. So the solubility parameter is important because there are tables of solubility parameters out there. And solubility parameter is the most common way to calculate chi, or the Flory-Huggins interaction parameter. So this solubility parameter part is important, and we'll work with solubility parameters a lot in this part. And solubility parameter sort of sounds like what? Sort of sounds like I'm dissolving one thing in another thing, right? Or how soluble is this system going to be? So in the name, it sort of tells you what's interesting about this property. And people have measured solubility parameters for lots of different stuff. And so you can look up tables of solubility parameters, and that gives you an idea of what's chemically similar to another thing where you might have a chance at dissolving it. All right. So if we take the solubility parameter and extend it to the delta H of mixing, because we're talking about all interactions or intermolecular interactions here. So we're talking about the delta H part. We get an expression that looks like this. So we get molar volume of the mixture. What's phi 1 and phi 2? Volume fractions. That's really important. And then what we have here is we have the difference in solubility parameters for component 1 and component 2. And then we take that difference and square it. And so everything in this expression is going to be positive when we think about solubility parameter. And we'll talk about what that means in a second. Let's see. Mixing becomes more favorable. Yeah. So if you look mathematically at this expression, when delta 1 and delta 2, when they're close together, you've got a very small solubility parameter difference. And so you'll have a small positive delta HM. When delta 1 and delta 2 are the same number, what is delta HM? I heard it. Go ahead, say it louder. 0. And if delta HM is 0, what are we back to in terms of what type of solution? Ideal, except for the fact that polymers and solvent molecules are different sizes. But when we don't have any delta HM mixing, we're getting more back towards ideal solution. And if delta 1 and delta 2 are the same number, that means that the intermolecular interactions in substance 1, substance 2, and the mixture are all the same, right? So there's no delta H. So that sort of checks out with what we know. It's just introducing this new mathematical expression to figure out what the delta HM mixing is. Oh, we already did that. So the one thing that solubility parameter doesn't do well is deltas don't have good H bonding characterization. And we'll see an example of that water has a really high solubility parameter, but it still dissolves some polymers like polynipam and polyethylene oxide that have a low solubility parameter. So water is the hard one to get because of this hydrogen bonding interaction. Solubility parameters are much better with dispersion or relatively nonpolar interactions. So you have to keep an eye out for some of those exceptions. Really polar molecules, or especially water, solubility parameter doesn't do well with. All right, let's see. Okay, we already talked about that. So now that we've talked about solubility parameters a ton, you usually find them in a table that looks like this. And so you can see they have very strange units, but it's energy per volume, and that is the cohesive energy density. How much energy per volume do you have? Then it's the square root of that, because remember, cohesive energy density is delta squared. So that's going to be in energy over volume. And so when you take the square root of energy over volume, you get energy over volume to the 1/2, or cals per cubic centimeter and the square root of that. Sometimes that's written in very funny units, which is calories to the 1/2 times centimeters to the negative 3/2. That's a really strange unit, right? But you know that equals calories centimeter cubed to the 1/2. It's a lot easier for me to see this. You just have to remember that it's the same thing. So now we can look at our polymers, their solubility parameters for all different types of polymers. And we can look at our solvents, their solubility parameter for all different types of solvents. And we can start to ask which is going to be soluble in what polymer, or what's going to give me the best prediction of solubility. So we have a clicker question, so you can get out your clickers. Which would you predict is a better solvent for polyethylene oxide? N-hexane, carbon disulfide, and water. Polyethylene oxide has a solubility parameter of 9.9. And hexane is up here. Carbon disulfide is right here. And water is way out here. So based on this idea of delta H of mixing being low, is that the snow squall alert on someone's phone? Okay. It's not the fire alarm, so we don't have to leave. It's probably a good idea not to leave. So, oh,
There we go.
now it's on everyone's phone.
It's gonna be like popcorn.
You're safe in here. Okay, so based on delta HM being low, that means delta 1 is close to delta 2. So based on that prediction, you can ring in. I think we had about 50 last time. Which solvent will we predict is polyethylene oxide most soluble? Great, I've almost got that. And we pick carbon disulfide because its solubility parameter is really close. And by close, we're meaning 0.1, 0.2, 0.3, right? Something right in there. So the really tricky part about this is that water, as I told you, is hard to pick up in solubility parameter analysis because it doesn't take into account these specific hydrogen bonding interactions. So I will mostly ask you about things that you can read right off the table, but when you go into your advanced courses or you use solubility parameters to think about reaction mixtures and other solvents you should use for whatever chemical process you're working on, you need to remember that solubility parameters don't give you the entire story. There's other models that are better at the polar stuff. Yes.
I'm still confused why delta H can be negative.
Because so in reality, delta H can be negative when we have strong intermolecular interactions between the polymer and the solvent. However, this theory doesn't allow for delta H to be negative because of the way the mathematical formalism is described. So it's just delta H can be negative in reality, but it's a limitation of the theory that we're using to describe these mixtures. Yeah. That's tricky. We're not going to run across a lot of negative delta H cases, except when water's involved and we have really strong interactions. So you'll know when that happens. But solubility parameters, by definition, will only give you positive delta H's. All right. Okay, so as I said, lots of people have measured these, they've calculated them, they've come up with tables of them. This covers your first homework problem, or maybe your second homework problem. I can't remember which one it is. But estimation of solubility parameters can also be done based on functional groups, and this is called group contribution theory. It turns out that the most famous example of group contribution theory has been done for gas separation membranes. Turns out that there's a lot of membranes that separate oxygen from the air, or separate CO2 from nitrogen, or separate methane from nitrogen from methane. And the theory used to design those polymer membranes was based on group contribution theory. So that's really interesting. And so here's our solubility parameter right here. We have some sort of molar attraction constant, F sub I. That's given right here. We've got some sort of volume component, which is the given right here. And I'll show you how to do this calculation in a second. Polymer density, repeat unit molar mass, other things are in there. And so we can use this now to calculate based on whatever polymer we have. We can count up all the functional groups, and we can make this calculation for solubility parameter. So how many CH2 groups do we have in polystyrene? One, right? CH2, right there. How many CH groups do we have in polystyrene? CH regular groups, not CH aromatic. Well, it turns out we only have one CH group right here, right? We're going to count the aromatic rings differently. This is CH aromatic. How many of those do we have? 5. 1, 2, 3, 4, 5. How many aromatic rings do we have? 1. Aromatic rings are counted funny. You get 1 for carbon aromatics and 1 for a 6-membered ring. So these subscripts on here mean you need to sum up all the individual components for the group contribution theory. And I won't make this a clicker question. I'll just show you how it's done, and you can do it on the homework. Bless you. And so what we do is we know what the density of polystyrene is. So this is PS density. And we made our tally of all the different functional groups. And we multiply the F per mole here, or the solubility group contribution per mole. And we get these numbers right here. We sum those up. We plug it into this equation with the M0 of PS. And then we get a solubility parameter for that. And I don't even have the answer on here. Where is it? Ah, 8.9 cows to the 1/2. Centimeters to the -3/2. So you can do that contribution, or you can do that calculation and come up with the same thing. And we could check this against our table of solubility parameters. And I think that polystyrene is probably on here somewhere. This was measured, and so that's 9.1 cals per centimeter cubed to the 1/2. So that's not too different from 8.9. So you can go home and read about this group contribution theory and make sure you can do the sum. I think you're going to have to try it on your homework. And so you just have to have good counting for how many functional groups you have and be able to interpret all this different nomenclature. And I'll help you through it. This is just one example right here for polystyrene to make sure we're counting correctly. Any questions or comments on that? Yes.
What's the C double bond, like the fifth entry? How is that one?
This is for this one right here.
Yeah.
So this is for any aromatic. And then you add the ring part. So there will be an entry for a 4-membered ring. There will be an entry for a 5-membered ring. And so it's really the combination of these two that describe that 6-membered aromatic ring, because it's all counted as one functional group for that ring, because all the carbons are aromatized, so they work together. Yeah. Now, it can get complicated, and I won't make them too complicated. Polystyrene will be about the most complicated that it gets. But you can see all the different, you can see ethers here, right? Here's double bonded carbon, right? Let's see, we've got nitriles, we have primary amines, so you could sort of pick out based on the molecule you're interested in. You see that C6H4 has a little bit different solubility parameter than just the CH. And so it's going to really depend on how you parse the molecules. And like I said, I'll make the examples reasonable. Yes.
So delta 1 and delta 2, if we compare them, what would be a good difference between them, for example, to make the polymer soluble in the solid?
Yeah, you want the difference between the solubility parameters to be about 0.1 or 0.2 or 0.3. So closer is better. Once it gets to be 0.4 or 0.5 difference between the two deltas, you start to get polymers that are less soluble. But we could talk about, say, something like polyethylene oxide and its solubility, let's not do ethanol, in ethyl acetate versus carbon disulfide. So what solvent is polyethylene oxide more soluble in, carbon disulfide or ethyl acetate? Carbon disulfide, right? The solubility parameter is closer. So is the coil of polyethylene oxide bigger or smaller in carbon disulfide compared to ethyl acetate? Bigger. It's more stretched out. So this doesn't necessarily say that polyethylene oxide is not soluble in ethyl acetate, because we don't have a rule of thumb for absolute no solubility, but we can easily say that the coil of polyethylene oxide is contracted in ethyl acetate compared to carbon disulfide, because its solubility parameter has a bigger difference, and so there's not as many solvent polymer interactions. So we can use the table like that for sure to talk about how many polymer solvent interactions there are. Does that make sense? Great. All right, a couple more slides. So now we get to the Florey-Huggins interaction parameter, because we said that chi has something to do with the enthalpy part. And so this is our expression for the Florey-Huggins interaction parameter in terms of the solubility parameter. So this is delta G of mixing in Florey-Huggins. And we know volume fractions, we can count number of moles, all that stuff. And we just need an expression for chi. And so based on all of these solubility parameters, you can use these right away to calculate chi for Florey-Huggins interaction parameter. So now if you know the volume fractions, you know what the components are, you can look up the solubility parameters, you can get the full accounting for what the delta G of mixing is in Florey-Huggins theory with the solubility parameters. And since these values are available and they're tabulated for a bunch of different solvents and polymers, this is a very common expression for getting chi in Florey-Huggins. All right, last clicker question. If the difference in solubility parameters increases, then what can be said about delta G of mixing? So we're talking about this difference going up. What's going to happen to the delta G of mixing? We know as the difference goes up, what is likely to happen? It's a less soluble mixture, right? And if something is less soluble, what's going to happen to delta G of mixing? Delta G of mixing is going to increase. And so this is the connection we want to make over the next few lectures, thinking about solubility parameters, intermolecular interactions, entropy of mixing, and then finally Fourier-Hugget. Thank you very much. See you on Wednesday.